Alright, we're going to look at section 4.3. So, section, oops, let me use a color here I can write with. So, section 4.3. This is the mean value theorem. And monotonicity. Okay. So first what we're going to do is we're going to write out the mean value theorem. Then we'll draw a couple pictures to take a look at it. And then we'll do a few examples. So we're going to say theorem, mean value theorem. Okay, so things kind of weird. We're going to say assume that f of x is continuous on the closed interval a to b. And then we're going to assume it's differentiable on open interval a to b. So assume it's continuous on closed interval a to b and differentiable on open interval a to b. So if that happens, then there exists at least one value c and c is going to be in the open interval a to b such that the following thing happens. We get f prime of c, so the instantaneous rate of change at c is equal to the average rate of change from a to b. Okay, so that's our theorem. And we're going to kind of draw a picture to see what it's talking about. So let's say we had some sort of, let's draw a picture here. Let's say we had some sort of line that's, I don't know, doing something like that, I guess. And let's say here's A, and out here is B. So if we look at the right-hand side of the mean value theorem, f of B minus f of A, all that over B minus A. If here's A and here's B, what it's saying is if we draw the slope of the secant line between A and B, so the slope of that line would be the average rate of change from A to B. So this line right here, slope of the red line, we could say that's the secant line from A to B. Is this equation f of b minus f of a, all that over b minus a. So that's the right-hand side of the mean value theorem. What the mean value theorem says is if you have some line like this, then you're guaranteed there's at least one point where the first derivative at that point is the same. And if you remember, the first derivative is the slope of the tangent line. So what we're saying is the mean value theorem is going to guarantee that there's at least one tangent line that has the same slope as the average rate of change from A to B, or the slope of the secant line from A to B. So here's slope of secant line from A to B. As long as the function's continuous and differentiable over the interval, then you're guaranteed that there's at least one basically one point whose tangent line is parallel to the secant line from A to B. It's another way we could say it. So let's do a problem with it, and then let's see a couple other things from it. So for our first example, we want to verify, and the book says MVT for mean value theorem. So we want to verify mean value theorem with f of x equals square root of x, and a is 1 and b is 9. So what I'm going to do is, mean value theorem again says that there's some c, f prime of c is going to equal f of b minus f of a, all that over b minus a. So since we got a and b, let's figure out what the right hand side would be. F of b would be square root of b, which is 9, minus f of a would be square root of a, which is 1, all that over 9 minus 1. So square root of 9 is 3 minus 1 over 8. So that's 2 over 8, so 2/8, which is 1/4 if we reduce it. So the right-hand side of our equation is 1/4. So to verify the mean value theorem, we need to show that the first derivative, there is some c value in between 1 and 9 that has a tangent line with slope of 1/4. So how we're going to do that is we're going to take the derivative. So if this one here is square root of x, the derivative will be equal to 1/2 x to the negative 1/2. That's our derivative, and we're going to set that derivative equal to 1/4. So we'll say, if I replace the x with the c to make the letters line up, is this a solvable problem? Can I set the first derivative equal to the right-hand side over here and get some c value that solves it? So let's see here. The 2 would multiply across. So we get c to the negative 1/2, which, to make it easier for me, I'm going to say that's 1 over square root of c. And 2/4 reduces down to 1/2. I guess we can cross multiply and get 2 equals square root of c. And we'll square both sides and get 4 is c. So f prime of 4 equals f of 9 minus f of 1, all that over 9 minus 1, and 4 is an element of the open interval 1 up to 9 like we wanted. And so we've done work here to show that yes, the mean value theorem is verified. For that scenario, we're looking between 1 and 9 with f of x equaling the square root function. There does exist some c, particularly c is 4, where the first derivative evaluated at 4 will make everything work out. Okay, there's a similar statement that we can get a corollary to that mean value theorem, so we're going to write it out. We're going to say if f of x is differentiable and, so if the function itself is differentiable and your first derivative equals 0 for all x from a to b, then f of x is constant on a to b. So what this means is that basically if you have a region and the first derivative is 0 for the whole region, then the function it came from was f of x equals just a number, like f of x equals 7 or something like that. If you remember, derivatives of numbers go to 0, so this is saying if there's a region where the first derivative is 0 for the whole region, then f of x is constant on that whole region. Okay, we're going to define a couple things here, and then we'll do the rest of it in another part. So we're going to say I'm going to define what it means, increasing and decreasing behavioral functions. So we're going to say f of x is, we'll say, increasing on the interval a to b if whenever f of x1 is less than f of x2, so if the function at x1 is smaller than the function at x2 for all x1 and x2 in AB, such that x1 is to the left of x2, which means x1 is less than x2. So basically, for all points, every time in the region AB, if all your points x1, which are to the left of x2, if the left-hand point always has a smaller y value than the right-hand point, then the function is increasing. That would mean it's some sort of shape like that, where for any point that we say, if x1 is to the left of x2, then x1's y value will be here, and x2's y value will be bigger. And you can kind of see, as long as x1's on the left, if it slides a little bit further or a little bit closer, as long as x1's on the left of x2, x1's y value will be smaller than x2's y value. So we're going to say we're decreasing on a to b if f of x1 is greater than f of x2 for all x1 and x2 elements of the interval a to b, such that, and we still want x1 to be to the left of x2. So this time we're saying if you have a region of x's, and if x1 is to the left of x2, and for all the x1s on the left, their y values are bigger, so all the x2s on the right have the smaller y value, then we say the function is decreasing. So you guys should have defined those back in Algebra 2 and doing it again in pre-cal. Just kind of a quick reminder. Basically, if you look at, as you move from left to right across the graph, if the y's get bigger, it's increasing. If you move from left to right across the graph and the y's get smaller, it's decreasing. And again, you just kind of think if every time I have an x value to the left, if the y value is smaller than an x2 on the right, then it's increasing. If I have an x1 on the left and x2 is on the right, and every time x1's on the left, the y value is bigger than x2, then the function will be decreasing. Okay, so we're gonna we'll do the rest of this thing here in another part.